Hi, and welcome back. We're about to start our Chapter 2 topic, which is periodic table. And as with Chapter 1, we're going to be reviewing a lot of concepts that should be familiar to you and just adding in a little bit of extra detail that helps us explain at this level how these phenomena come about and the structure of the atom and how it relates back to it when we look at the periodic table. Remember that at all times when you're studying chemistry and in every test for chemistry and exam, you will have access to a periodic table. So it's important to know your way around it, know what information that we can get from it. So essentially in 1869, Dmitry Mendeleev created what we consider to be the modern periodic table. He proposed what we call the periodic law, and that is that the properties of the elements are periodic. They follow a pattern, and this follows according to a pattern of their relative atomic mass. This was a little bit off, and we'll talk about that a little bit later on. But the modern periodic table itself is based off atomic number, not atomic mass, and this is one of the ways it's changed since Mendeleev's time. He arranged the elements according to increasing order of their relative atomic masses and the periodicity of their properties, i.e., he grouped them according to ones that had similar chemical properties, but put them in order from smallest atomic mass to largest. It is important to note that during Mendeleev's time, the electron was not known to exist, and we had no idea of isotopes because the neutron had also not been discovered at this point in time. One of the things that made Mendeleev's periodic table quite unique and superseded the ways of cataloguing atoms prior to Mendeleev was that he left gaps for elements that, based on his theory, he predicted should exist even though they hadn't been discovered yet. So if we look at this periodic table here, this is actually a picture of a periodic table that is the same as Mendeleev's. He arranged elements in vertical columns called groups, which we maintain today, and the elements in horizontal rows that we refer to as periods. He went from smallest to highest atomic mass and then made predictions for elements that should exist. So we can see here that there are gaps in this table, and this is due to those predictions. One of the things that didn't exist and wasn't known in Mendeleev's time also was the noble gases. Because they were unreactive, they hadn't been discovered at this point in time. So following on from Mendeleev, there were a number of notable discoveries that pushed our understanding of chemistry forward. You don't need to know the dates or the people in particular, but you should have a general idea of how the knowledge was built up over time. That is in 1892, so almost 30 years after Mendeleev, Rayleigh and Ramsay discovered the noble gases, which had not been known up until this point. In 1913, Henry Moseley, following the discovery of protons and the idea of atomic number, rearranged the periodic table to be in order of atomic number rather than atomic mass. This made a couple of changes in the heavier elements where the presence of isotopes caused the mass to be greater than the number of protons. So a couple of elements ended up swapping place. In 1944, Theodore Seaborg added in our actinides. So the 14 elements that are heavier than actinium go into a separate group. These are the actinides, and they are filling the F subshell. So they fill our F block. And then successfully managed to synthesize elements 94 to 100 by artificial transmutation. And this is by combining elements together, so colliding protons and neutrons together in order to make larger nuclei. So everything post 93 is an artificially created element. So essentially, the periodic table is simply a way for chemists to be able to catalog all the known elements and to organize it in such a way that we can have a large amount of information readily in a very simple and easy to understand tool. It's incredibly powerful if you understand how it's arranged, and what that means. So it provides a huge amount of information in one compact space, and in fact, the shape and the way that it's arranged today is simply so it fits on one page. So those actinides and lanthanides being pulled out are so that the table isn't too long and it's usable on a single page. It means that we can minimize the memory of individual facts for each element. So by having a tool that allows us to reference similarities and differences, predict trends and other things like that, we don't have to remember as much, okay? It reduces the cognitive load and allows us to have better understanding of how things will behave and make more predictions rather than spending that brain space memorizing atomic masses and things like that. It allows us to organize that knowledge, and it allows us to extrapolate and build on known facts to predict the properties of new compounds, how things might bond together and how they might behave, which is what will be the focus of our studies this year, is being able to understand what bonding means in terms of how materials will behave, what properties they will have, what kind of reactions that we could carry out with them. So with the basic organization of the periodic table, you should be familiar with this. Our horizontal rows are our periods, and we have period 1, 2, 3, 4, 5, 6, 7. Okay, so periods 1 through 7. They have period numbers equivalent to the outermost shell. So something that is in period 2 will have its valence electrons in shell 2. Okay, if it's in period 3, the outermost shell would be shell 3. Groups are the vertical columns in the table. Okay, these contain elements with the same outer shell configuration. So in group 1, this is in our S block, so it will have one valence electron in an S subshell. Okay, in group 2, they will have 2 valence electrons, group 13, 3 valence electrons, group 14, 4, and so forth to 18, which is our noble gases, which has 8 valence electrons. Okay, so our groups give us our valence electron structure. Because they have the same number of valence electrons, they will behave in a similar fashion. So groups have similar chemical properties. In modern periodic tables, they should always be numbered 1 through 18. In some older periodic tables, you may see these groups here being labeled different and the main group elements being labeled in Roman numerals. The use of Roman numerals is no longer the international standard, and the groups of the periodic table should always be numbered 1 through 18. In this case, the numbers that are equivalent to the number of outer shell electrons form the unit of the digit of these groups. So for group 13 to 18, 13 has 3 valence electrons, 14 has 4 valence electrons, and so forth. So with this, we need to wonder why the element's properties are periodic, i.e., why do we see this repeating pattern where we can put them in to 18 columns, or that every 8 valence electrons we seem to see a repeating pattern of the properties. These properties that we see periodic trends in include melting point, conductivity, reactivity, and the type of compounds they form when reacted together. All of these properties are dependent on their electron configuration, so that repeating nature of forming 8 electrons in the outer shell as a stable octet, that continues to repeat, so we see a repeat of these properties. So the regular pattern of similar electron configurations is observed as the atomic number increases, and this gives rise to our observed periodicity. So based on this, we can link our electron configurations to our periodic table structure. The S block is groups 1 and 2. These will have electrons going into S subshells. The P block have electrons going into P subshells. D block, the electrons are being placed into D subshells, and then the F block into F. These blocks, S and P together, form the main group or main block elements. D block is our transition metals. P block also contains our halogens, which are group 17, and our noble gases, which are group 18. And then for group 1, we have our alkaline metals and our alkaline earth metals. These are special groups that you should be familiar with. The idea that group 17 is the halogens, group 18 is the noble gases, where the lanthanides and actinides are located. So, as we said, the idea that these trends repeat every period or have periodicity is a result of the electron configuration. And because elements in the same group have similar properties, this is mostly true, though there is some variation in our non-metal groups. This is because of a similar valence shell configuration. Groups 1, 2, 17, and 18 all can either contain all metals or all non-metals. So this idea that the entirety of the group will react in a similar way is more significant in these groups. If we look at group 13 and 16, though, these contain both metal and non-metal, so there is variation in properties observed in these groups. When we move across the period, we observe significant changes in properties, okay? And the main reasons for this is effective nuclear charge, which we'll be looking at in our next video. So this is just an idea of the structure of our periodic table, the idea of groups versus periods, the special names of those groups and periods, and then how we can name those and what information we can get from it. I hope that this has refreshed your memory on some of that, and I'll see you in class.